Hello, my name is Christopher, and this video is a summary of my master thesis, which is called Transferring Deep Reinforcement Learning from a Game Engine Simulation for Robots. That sounds like quite a mouthful, so let me just try to tell you what it's all about. First of all, what is deep reinforcement learning? Well, deep reinforcement learning is machine learning using a neural network that learns from its past experiences. An example of this is the mountain car game from OpenAI Gym. In this game, the mountain car has to come from the bottom of the hill to the top of the hill to reach the goal. It can't just drive forward, it has to drive back and forwards, gaining momentum. Using deep reinforcement learning, it tries again and again and again, learning from its past experiences, and then in the end, it's able to perform the task consistently. So in this project, the focus is to use deep reinforcement learning for robots. One of the implications of using deep reinforcement learning is that the amount of experiences that the robot needs in order to learn is quite a lot. Therefore, it can take a really long time to teach the robot what to do, and that could cost a lot of resources as that potentially expensive robot is used for quite a long time. A way Google got out of this problem was to use many robots, and then they will each gather experience for the deep reinforcement learning algorithm. This is not feasible for many researchers, as these robots are potentially very expensive and they can also damage themselves and things around it when using different actions to learn from. So how do we fix this issue? Well, the issue has actually come up in other fields before. For example, if you want to design a wing and test the air resistance of the wing, would you then build a whole plane and then send it up without having the plane tested at all? No, you would do something a lot better, which we call simulations. So why do we need simulations? Well, in the previous example, the wing could be tested for air resistance and how well it did with airflow by using a wind tunnel. We can also use simulations for robots to train them in a very safe environment. They can't damage themselves or other things around them. The simulation can also be sped up so that it will gather experience faster, and then it will be able to learn quicker by that. So for this project, we want to use a simulation to teach a robot a task using deep reinforcement learning. However, this has already been done before, so let's take a look at those first and then see what we're doing differently. As an example, Lei Tai and their research team has trained a robot to perform mapless navigation by training them in a simulation. This simulation is called VRAP. Another example is Yu Chen. Yu Chen were able to train a robot to be socially aware while navigating through a crowd of people. Both these research papers used laser scanners or a calculation of distance to objects around it in order to learn how to navigate in their environment. So no actual image data was used, and that's what we're looking into in this project. Because images of the world is really important in some applications for deep reinforcement learning, especially some robots. Examples of this is a self-driving car, for example. It makes a very big difference if the object in front of it is another car, a pedestrian, maybe a stick on the road, or even a wall. It has to make different decisions for each object in front of it. So it needs to have a very clear understanding of what exactly is in front of it. And to do that, it needs images of those objects and learn from that. Another example is a weed detection system for agriculture. A machine driving around looking for weed needs to be able to see exactly what plant is in front of it. So an image of the plant is needed, or else it can't detect the real plant. Even a simple task for humans, such as grasping an object and lifting it off a table, needs precise image data for the robot so it can generalize on the objects and know where to grasp them. To overcome the cost of using real robots for deep reinforcement learning, and also the lack of realism in current simulators, a simulation with high rendering capabilities and lighting capabilities are needed to replicate the real world properly. Such a simulator could be a game engine. Modern game engines are made to simulate the world and with the highly realistic graphics and highly realistic physics as well. The Unity 3D game engine is able to render highly realistic environments in real time. This is, for example, from a demo reel of the Atom episode, which is rendered in real time in Unity 3D. So what did I do for this thesis? Well, first of all, I simulated a robot in the Unity 3D game engine. I then made a communication with the ROS, which were able to remotely control that simulated robot. I then used deep reinforcement learning to teach that robot to perform a simple task. And then I transferred that learning to a real robot for that robot to perform the same task. But let's take that again, just step by step. The robot that I chose to simulate in Unity 3D was a very simple Turtlebot 2 robot, which has the capability of driving around, and it also has a PrimeSense camera to see with. The Turtlebot 2 was simulated in the Unity 3D game engine, and an environment was created for it with a small blue ball in it. The task that I wanted to teach it was to find the ball and drive into it. This sounds like a simple task, but when the raw pixel data from the camera is the only knowledge the robot has of the environment, the learning becomes a bit tricky. So how did the robot learn how to do it? The learning was performed by a deep neural network, which takes in an image of the robot, analyzes that image, and then through the network estimates the best possible action for it to take. It then sent that action to the robot. But how did the robot receive that action? Well, that was done by the aforementioned communication with ROS. ROS, or Robot Operating System, is a middleware used to control robots remotely. In my case, the robot sends an image and also a corresponding reward to the deep reinforcement learning algorithm. The neural network then sends the best estimated action back to the robot through the ROS connection. The robot then performs that action and then sends an image back again. This loops many times until the robot has learned to perform its action, or perform its task. After 10,322 tries, which took around 29.5 hours, the simulated robot was able to hit the blue ball 200 times in a row. The robot was able to search for the ball and drive into it consistently, only with the raw pixel data of a small 80x60 image. No pre-trained convolutional neural network were used for any object detection. The model of the reinforcement learning algorithm was saved so that the learning could be applied to a real robot. The saved model was then used for a real robot to perform the exact same task as the simulated robot. The real Turtlebot 2 was not able to perform the task. It could not find the ball and drive into it. In fact, most of the time it just moved back and forth with no real progress. Only at one point was it able to perceive the ball and drive towards it. We hypothesized that the reason why it was able to find the ball and drive towards it there was because that the white wall behind it and the white floor was very similar to the ones in the simulated environment. However, the test was not all about transferring the learning from the simulated robot to the real robot. It was also about how easy it was to change the simulated robot with the real robot. In this project, the simulated environment was created such that the control of the robot was exactly the same as controlling a real robot. That meant that I only had to cut the communication of the simulated robot and then connect to the real robot. Then it would work in the exact same way as the simulated one did. This project shows the plug-and-play capabilities of using a game engine to simulate robots for deep reinforcement learning. The simulated robot and the real robot were easily interchangeable. So therefore it shows that the use of game engines in simulating robots are very promising. We believe that for future work we need to have a very highly realistic simulation of the real environment for the reinforcement learning to be transferable to the real robot. thank you for listening. I've been Christopher Brede Lillelund, and I hope you enjoyed this summary of my master thesis.